Hey, everybody. I'm not sure if people have picked up on it or not, because this is like the first time that I've explicitly mentioned it. But kind of how I structure my research is like during the week, I try to focus much more on like business oriented things and things that honestly, like I like to eat food and I have kids. So I try to focus on things that like drive that forward. And then during the weekends, I try to focus on things that are more about like physics and my moonshot type of projects. And then generally speaking, with my moonshot type projects, I get let's say I run like over a common weekend. I think of like maybe like 5 or 6 like out there ideas, right? And I run it, and then like maybe out of that, like one of them pans out, and then I make a video out of that. And then my rest of my videos throughout the week are just different things, right? Uh, it just happens that this weekend, it's just a lot of these are panning out. And then so I released this MIT license. It's available. So I have a research paper. I've released it also on Substack, and then I GitHub repository. And then in this video, I'll walk you through my Colab experiments. So this is self-repairing neural networks, artificial sleep as a mechanism for long-term AI stability. As far as the abstract, modern deep learning models suffer from catastrophic forgetting, performance degradation, and increasing computational inefficiency over long-term operation. They degrade over time, and we don't necessarily know why. Inspired by biological sleep cycles, we introduce artificial sleep, an adaptive mechanism that detects neural degradation and autonomously repairs itself through structured optimization processes, memory consolidation, and, when necessary, full resets. This paper details the experimental validation of a self-repairing LLM demonstrating resilience against performance decay and concept drift. We release our findings under the MIT license with a publicly available implementation on GitHub. Essentially, overall, kind of what we know about the drift process is within models is that like they'll degrade over time and their inputs will drift further apart than original inputs. And what I do, and when I combine that with kind of my logic with regards towards biological systems, I reach one conclusion with biological systems, which is that every single biological system sleeps, and we don't necessarily know why every biological system sleeps, but every biological system can also be classified as a closed system, which is also how a neural network can be classified, right? And then so within that, it's 100% known that every biological system, closed system, has ways to excrete waste from the system. So sleep is often thought to like repair the system and to be thought of within self-repair. So I just thought of that concept, right? So we know 100% that these models, they degrade quickly and far more quickly than we would ever expect. And no one knows why. And they don't sleep. And so I just put that correlation together, and then let me create a system for the model that is like artificial sleep. And I acknowledge up front, right? This is generation one. I'm not a doctor. I'm more of an engineer. I suck at biology and all of this, right? Like this is, I went through and I experimented with this from an engineer perspective. So I just went through like, and brute forced it like 50 times until something popped out of it and it actually worked. Like, I don't know the biological, the psychological, a lot of other elements can be added on top of this. Like, so this is Gen 1 research. It's fully available for anyone. This is free, open source, MIT, everything associated with this MIT license. Let's dive into it. Introduction. Artificial intelligence models, particularly LLMs, exhibit performance degradation over extended use. This degradation is marked by increasing perplexity, repetitive outputs, and structural breakdowns. Current methods to address this include fine-tuning, continual learning, and manual intervention. But these approaches are costly, computationally expensive, and most importantly, often ineffective at preventing gradual drift. This work presents artificial sleep, a self-repairing neural mechanism inspired by biological sleep. The approach combines perplexity-based degradation detection, weight decay-based soft optimization, adaptive memory consolidation, attention cleanup mechanisms, and automated model resets in extreme conditions. Methodology. Model setup. We employ Hugging Face small LLM 2 135M, my favorite model on the planet, thank you. A compact open weight transformer model as our base test system. Performance metrics to measure degradation and recovery. We track perplexity, which is a measure of output randomness, repetition ratio, a measure for linguistic diversity, and completion validity, the frequency of grammatically valid sentence termination. 2.3, the sleep cycle algorithm that the artificial sleep cycle runs at adaptive intervals and consists of perplexity thresholding, gradual weight adjustment, attention cleanup, memory consolidation, and emergency model reset. This is like translating biological processes to me as an engineer that knows nothing about these, like purely like in thinking about it in computational engineering terms to what this would look like for a model. And like, so experimental results, baseline performance, initial outputs show low perplexity, so within the 4 to 6 range with stable linguistic structure. And then I introduce progressive degradation. So without intervention, the model degrades by iteration 6 through 9, with perplexity spiking to 49 plus, leading to nonsensical and repetitive outputs. Then the self-repair mechanism kicks in through sleep cycles, and then after intervention, degradation slows by iteration 10 through 12. Meaningful text reemerges around iteration 13 through 15, and then the model corrects itself, and we have beautiful outputs again by 19 and 20. So future directions and future research would just my recommendations. AI degradation is detectable in real time through perplexity trends. Structured sleep cycles enable long-term stability. Emergency resets prevent catastrophic collapse without full training. As far as next steps, recommendations again, implement dynamic sleep scheduling, expand experiments to for multimodal models, and then we can integrate swarm principles. Again, this is all open source for everyone. Let's dive into the code here, the Colab code. So I run through a bunch of experiments, right? And then so my first thought is I'll just measure entropy and then track entropy within this. And then if I can track entropy and then like adjust entropy, then it'll be cool. I thought this would be really maybe quick, right? And then so I do that, and then I just run it through the inputs over time. And what I can see is, interestingly, so I want to highlight this, right? Like, so this is without, this is just tracking the entropy. So the first input of the model, like the entropy in the model is going down over time. So like this is my assumption is accurate within this, right? Like if you're utilizing this model just like repeatedly and like just throwing inputs at it, like entropy degrades over time as you're throwing inputs at it. And then so I can prove that like 1,000,000%, right? But then what happens is so then I measure it, and then I'm like at this point I have completely different logic for like the sleep mechanism. I'm like pruning the model, like a whole bunch of different stuff, and then like the second that I do it, it just like we get garbage outputs, right? Garbage, and then the model never corrects the outputs, but I'm like able to like stabilize entropy through the sleep, right? Like that's what we can see is that like without sleep, artificial sleep, there like entropy is just decreasing, and then here's like when I kick in, it's like okay, put the model to sleep around iteration 5, and then you can see it stabilizes to like around iteration 5. It never like crashes, it almost does, right? But we're able to stabilize it up, but those outputs just suck. But we're able to fix the entropy loss that we can 100% track as occurring there, right? So then the next step is like, okay, we're tracking entropy, and I know that entropy is in here, but we need more levers. It's not just entropy going on. So let's like essentially adjust the way that we go about this, and let's add like memory consolidation. So this is where I improve the sleep cycle. So essentially I start having the model like replay memories in its head as it sleeps. Like I go through like all of the processes that are a part of that I know of with biological sleep mechanisms. Uh, and I essentially introduce that, and then I introduce, this is where I start introducing like more of the metrics, right? So I have the repetition ratio and perplexity that I'm measuring as opposed to entropy. And then what ends up happening is like the same thing, right? I put it to sleep, and then it destroys the model, and then but what happens is that perplexity just goes through the roof. Like when I put it to sleep, and it recovers, right? So like it goes like, so it's, I mean, perplexity is, before this it's like 5, like 5, and then I put it to sleep because it's going up. Perplexity is increasing as entropy is decreasing, which would be expected, right? So like something, the model needs to cleanse itself. I know I'm on the right track here, but I can't control it right at this point, and then so I just like, perplexity explodes. And then it goes to 33, but it's still a lot higher than 5. And we do get better outputs off of the 33, right? Like this is just pure garbage. But then once perplexity goes down a bit, down to 33, like you can see the dial like adjusting back, right? This is still bad because 33 compared to 5, that's magnitudes higher, right? Like 5, 10, 15, 20, 25, 30. There's a lot to get up there. But this is magnitudes better than 1350 though, right? And we can see it at dialing back closer to 5 there, and then but then that's the best that we get, and then we get 41, and then it explodes back up. And at this point I'm not understanding how to, like, oh, here's a good one, 20, right? And then like, again, the closer that it's getting down to 5, we're getting like more meaningful outputs. So what is the meaning of life? Belong, pose, belong, mostly belonged, belong, mostly, usually, mostly belonged. But that's a lot better than regular, annually, like, which is a lot better than the perplexity up here, which is like not even like English on and for most of it, right? And so you can see how that lever is getting thrown off. I'm hoping that this is a good illustration for you. Like, so this one, like when we get to this one at like 3,000, it's measuring, like it's putting in exclamation points and just random like gibberish, right? And then, but if we get it back down to like 35, it's like, it's not pure random gibberish. It's mostly threat, mostly usually threat, question, mostly question, mostly usually vi. It's all English words, and it could be in almost sentences, because it's like we're our dial is not fully there. And then that's what I'm showing here, right? So I can see, like, I can control these. I'm starting to be able to control the, like, I can't control the dial at this point, right? Bottom line, right? We get massive spikes and it's all throughout, but I realize that there's a dial here, and then so I'm starting to be able to dial it, and this is massive spikes, right? Just like this model is going crazy still, but can I dial it? And then so that's what I'm trying to do, and then so just a bunch of these over time. Like usually I prune these notebooks and these experiments down, but I'll show you. Like, so I went through a bunch of iterations, right? And you can see getting a little bit better, much better, right? And then so then we go here. This is the last experiment, and then this is essentially where we get a self. And so the model, we get that. Around epoch 8, it goes at epoch 8 exactly. The model is like the worst, and we see perplexity goes up to 50, is the worst that it goes up to in this instance, and then like those spikes on this graph would be 25, whereas like on this graph that we're looking at here, this one right before it, kind of like how graphs can fool you if you just look at graphs, right? So this is like 300 and 600. So on this graph, if we're looking at it, the peak would be here on this graph. So we are a significant improvement, and this is significant improvement over the first one, right? So while this this is still looking like, whoa, it's still a massive peak. Like look at where the massive peak is. It's a 50 is the score of that massive peak, which would be a blip, and not even a blip on the first one. And then same thing with this repetition ratio over time. Like it's we are able to. This is far more dialed, right? It's we do have the spikes and around the dips where essentially we have. Kind of like chaos introduced into the model around perplexity 8, but then it's fully self-correcting, and then really very stably back towards baseline perplexity. intensity, right? And then the model, so in this instance, the sleep cycle is kicking in. It's forcing, like, so if there's like a lot of deviation in the measured metrics, force the model to sleep. And then so that's what happens at iteration 8, right? It's like, or iteration 6, it forces it into sleep. And then iteration 7 is bad, iteration 8 is bad, goes through resets, and then it goes through its full sleep cycle, essentially ends at cycle 10, and then never goes to sleep again, like never kicks it back. At that point, I'll run it. I can run it, further, and it would go to sleep, and then it would essentially balance out over that, right? But it never, like, initially it's kicks in at cycle 6. We let it run for 10 cycles after it goes to sleep, and then it never kicks the sleep cycle back. So that's a successful experiment there. And we can see with our actual outputs, right? So our prompts explain quantum mechanics, response explain quantum mechanics, why it's important to understand and why it can be a bit tough. The first part of this series is on the history of quantum mechanics. You'll learn about the first experiments that showed the quantum theory is really true, et cetera, et cetera. Like, and then these are very good outputs, right? By iteration 19 and 20. And this is, again, small LLM 156. So I'm getting like better than the original outputs once the model like heals, right? Tell me a story. Tell me a story from your life that you have been made that you've made yourself. I'm not so poor as to be a poor, but I'm a rich, and I'm very rich. That is the way I made myself. I've not been rich for long, but it is the way I made myself. It is the ways I made myself and the ways I made myself. But again, 156 million parameter model, right? And these are better than the baseline outputs, as we're showing here. So I'm happy beautifully overall with these results. And then if you want, here's the GitHub repository for artificial sleep. Again, please enhance this. I can't state it enough, right? This is just my thoughts that sleep and this sleep mechanism should work. This is my assumption would be that whatever artificial sleep ends up being is going to be far from this. It's just this is my puny engineer, computer science oriented mind of what the model needs as far as these biological processes that I don't understand. And then so if you like this type of content, please like and subscribe. Thank you very much.